Now let us see the stress components in 3D. So this is a cubical element, and we can see in each phase there are 3 stress components. And opposite phase having the same 3 stress components. So how many stress components are there? Opposite phases having same stress components, so we will not consider that. That is 3 phase into 3, so 9 stress components. If we talk about this phase, that is which is perpendicular to x, that is sigma xx is the normal stress and other two are shear stresses. So what are the 9 stress components? They can be expressed in form of matrix form, in a matrix form, that is sigma xx, tau xy, tau xz, tau yx, sigma yy, tau yz, tau zx, tau zy, sigma zz. So there are 3 normal stress components, that is diagonal components are normal stress components. So these three are normal stress component. These 3 are normal stress components. Other 6 are shear stress components. For this phase, sigma xx is normal stress and tau xy and tau xz, are shear stresses. Now we have just derived that complementary shear stresses are equal and opposite. That is, we can write tau xy is minus tau yx, tau xz is minus tau zx, and tau yz is minus tau zy. So these 6 stress components can be defined by 3 components. So there are 3 normal stress components, 3 normal and 3 shear stress. So 6 stress components can define the state of stress in a 3D component, 3D mechanical component. Now we shall talk about a very special case. So we have noted the 6 stress components. Actually there are 9, but this one and this one are same. Similarly this one and this one are same, so only one can define. So 3 normal stresses, 3 shear stresses can define the state of stress. Now we shall talk about a very special case which is called plane stress. When we will call it plane stress? When 2 opposite faces of a cubic element are free of any stress, it is called plane stress. That is, let us consider z-axis and the plane which is normal to z-axis. The plane which is normal to z-axis, that is this axis, this plane is normal to z-axis. So on this face and opposite to that face, that is this face, this is the opposite to, these are 2 opposite faces, and on these 2 opposite faces stress value is 0. When 2 opposite faces of a cubic element are free of any stress, it is called plane stress. That is, what is the existing stresses? That is sigma zz, that is 0, tau zx, this is tau zx is 0, and tau zy is also 0. So these stress components are 0. So what is the remaining stress components? That is sigma xx, comma sigma yy and tau xy. If tau xz is 0, then tau xz, sorry, if tau zx is 0, then tau xz will be also 0. Similarly, tau yz is also 0. So for plane stress, the existing stresses are these three stresses: sigma xx, sigma yy and tau yx. Now, how to represent a plane stress condition? So these three are existing stresses and we can represent them like this. This is a plane stress situation. Sigma xx. So this is sigma xx, sigma yy, sigma yy, and existing stress is tau xy. Tau xy, tau xy. This will be tau yx and this will be tau yx, where tau xy is minus tau yx. And in the diagram, this minus sign has been already taken care, because tau xy is positive here. It is providing counterclockwise, sorry, it is providing clockwise moment inside a point. It is providing clockwise moment inside a point, and tau yx is negative, as it is providing counterclockwise moment. So this is the plane stress. Another definition of plane stress is that if this is the xy plane, this is drawn in xy plane, then stress components perpendicular to that plane is 0. That is, when stress components perpendicular to the plane is 0, then it is also called plane stress condition. So another definition of plane stress is that stress components normal to that plane is also 0. Stress component normal to the plane is also 0. So we have drawn the state of stress for plane stress condition. Now let us examine the stress on a plane whose normal makes phi with x-axis for plane stress condition. So let me draw it once again. This is the plane stress condition. Sigma xx, sigma xx, sigma yy, sigma yy. Then this is tau xy, is also tau xy. Now this is tau yx and this is tau yx. So this is the plane stress situation. Now tau xy is equal to minus tau yx, and this minus sign represents they are equal and opposite. But in the free body diagram, tau yx is already opposite to tau xy, so we can consider here tau yx is also equal to tau xy. That is, instead of tau yx we can write here this is also tau xy, and this is also tau xy, because minus sign already taken care by the direction of rotation here. Now our objective is to determine the stress values on an arbitrary plane whose normal n makes an angle phi with x, Similar like biaxial stress condition. Similar like biaxial stress condition. So first of all, let me draw the free body diagram. Let me draw the free body diagram. And let me give a name to this section, to this free body diagram, A, B and C. So this is also A, B and C. Normal stress is sigma n and shear stress on the arbitrary plane is tau. But here we have to add, this is tau xy and this is also tau xy. This is also tau xy and this point is C and this angle is phi. This phi is along counterclockwise direction and counterclockwise rotation of plane is considered as positive. Counterclockwise direction, counterclockwise rotation of planes are positive. This is for plane because this plane is rotated by phi from the normal of this plane rotated by phi in counterclockwise direction from x. So this is about the free body diagram. Now we have to calculate what is value of sigma n. Before that, let me define the areas. That is, area of this plane is DAN, area of this plane is DAY and area of this plane is DAX. Similarly here DAX is DAN cos of phi and DAY is DAN sin of phi. Now make the force balance to get the values of sigma n and tau. First of all, what we will do, that is forces along normal direction. This is the normal direction. This is the normal direction is 0. So what we will get? We will get sigma n DAN minus sigma XX DAX cos of phi minus sigma YY DAY sin of phi plus tau xy DAX sin phi plus tau xy DAY cos of phi is 0. So from this we'll get what? Sigma n DAN is sigma XX DAN cos square phi plus sigma YY DAN sin square phi plus tau xy DAN sin phi cos phi plus, sorry, this will be minus, sorry, if we get that side this will get minus and this will be also minus tau xy DAN sin phi cos phi. So what will be the equation? Now let us go to the next page. sigma n is sigma xx cos square phi plus sigma yy, sigma yy sine square phi, then minus tau xy, 2 tau xy sin phi cos phi, 2 sin phi cos phi is sin 2 phi. So minus tau xy sin 2 phi. Now rearrange the equation, that is half sigma xx 1 2 cos square phi is 1 plus cos 2 phi plus half sigma yy 1 minus cos 2 phi minus tau xy sin 2 phi. That is sigma n becomes sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy by 2 cos of 2 phi minus tau xy sin 2 phi. For simplicity, we shall consider sigma xx plus sigma yy by 2 as sigma average. Sigma average, similar like biaxial stress. 6x sigma yy by 2 cos 2 phi minus tau xy sin 2 phi. Or sigma n minus sigma average, sigma n minus sigma average is sigma xx minus sigma yy by 2 cos 2 phi minus tau xy sin 2 phi. And let me give a number to this equation. This is equation number 1. This is equation number 1. Now let us calculate the shear stress. To do that, let me draw the free body diagram once again. This was sigma yy, this is sigma xx, tau xy, this is another tau xy, this is sigma n, and this is tau. This angle is phi, this is also phi, this is also phi. Now A, B and C. Now to get tau, we have to make force balance along AC, and which will be 0. That is tau DAN minus sigma xx DAX sin phi plus sigma yy DAY cos phi. For this shear stress tau xy, that will be minus tau xy DAX, I have to forget the areas. This is DAX, this is DAY, and this is DAN. Now into this will be cos phi, and for this that will be plus tau xy day, this one tau xy day into sine phi. This will be plus, that is 0. Now tau dan is sigma xx dan sine phi cos phi minus sigma yy dan sine phi cos phi plus tau xy dan cos square phi minus tau xy dan sine square phi. So tau becomes sigma xx half sigma xx sine 2 phi minus half sigma yy sine 2 phi plus tau xy cos square phi minus sine square phi is cos 2 phi. That is, tau becomes sigma xx minus sigma yy by 2 sine 2 phi plus tau xy cos 2 phi. And let me give this equation as equation number 2. Now here these are the long equations. So let me first write down equation 1. This was equation 1. Sigma n minus sigma average is sigma xx minus sigma yy by 2 sigma yy by 2 cos 2 phi minus tau xy sine 2 phi, and tau is sigma xx minus sigma yy by 2 sine 2 phi plus tau xy cos 2 phi, tau xy cos 2 phi. So these are equation 1 and 2. This is 2 and this is 1. Now similar like biaxial stress, make 1 square plus 2 square in both left hand and right hand side. What we will get? Sigma n minus sigma average square plus tau square, that you will get sigma xx minus sigma yy by 2 square cos square 2 phi plus tau xy square sine square 2 phi minus sigma xx minus sigma yy tau xy sine 2 phi cos 2 phi plus this will be sigma xx minus sigma yy by 2 sine square 2 phi plus tau xy cos square 2 phi plus sigma xx minus sigma yy tau xy sine 2 phi cos 2 phi. So these two becomes cancelled, and here sigma xx minus sigma yy by 2 whole square, if we take common, here will be another square. Cos square 2 phi plus sine square 2 phi is 1, and here also cos square 2 phi plus sine square 2 phi is 1. So ultimately what we will get, that is sigma n minus sigma average square plus tau square is sigma xx minus sigma yy by 2 whole square plus tau xy whole square. So same equation like biaxial stress, only tau xy square at right hand side has been added. So this equation, say equation number 3, is analogous to what? X minus a whole square plus y square is r square. Here a is sigma average. We know that this is a equation of circle in xy plane, because variables are x and y, xy plane. Whereas in equation 3 the variables are sigma n and tau. So A is sigma average, that is center of the circle is sigma average comma 0, center of the circle C. And what is radius here for the Mohr circle? This is the Mohr circle. Let me write down it clearly. This is Mohr circle for plane stress. This is equation of Mohr circle for plane stress. So equation of Mohr circle for plane stress, and what is the radius of the circle? That is root over sigma xx minus sigma yy by 2 square plus tau xy whole square. Now how to draw the Mohr circle? Now let us draw Mohr circle for plane stress. Mohr circle for plane stress. Mohr circle for plane stress. Take sigma n and tau plane. This is sigma n, abscissa is sigma n, and ordinate is tau. Now plot point A, whose coordinate is sigma xx comma tau xy. That is, point A represent state of stress at phi equal to 0 degree. Next, plot point B, and coordinate of point B is sigma yy comma tau yx. That is, point B represents state of stress at phi equal to 90 degree. Then join AB, and this point is C. That is the center of the Mohr circle. And now at center C and taking radius CA or CB, draw the circle. And this is the Mohr circle. Sorry, this should pass through B. So this is the Mohr circle. So this becomes Mohr circle. Now, if this is point D, and this line here, this line is phi equal to 0 degree. This line represents the state of stress at phi equal to 0 degree. So from CA, and if this is point D, an angle ACD is 2 phi. ACD is 2 phi. That is 2 phi. Then coordinate of D, that is, say this is O, A, B, C, D, E, this is F, this point is G, this is H, and this is I. Then OG, that is sigma coordinate of point D, OG is the tau n at phi. At plane phi means, sorry, this angle is 2 phi. Phi is the plane whose normal makes an angle phi to the x, and dg gives tau at phi. So this is the construction of Mohr circle. Now the question is, what is maximum and minimum normal stress for plane stress condition? Now let me define what is maximum and minimum normal stresses. Maximum and minimum normal stresses are called principal stresses. Principal stresses. Now let us find the value of principal stresses from Mohr circle. So first of all, let me draw the Mohr circle. This is sigma n, this is tau. Let me draw it first. This is the Mohr circle. Sorry. This is the Mohr circle on which this is point A, say, and this is point B. Is sigma xx comma tau xy. This is sigma yy comma tau yx. This point says C. Now this is E, this is F, this point is G, this is H, and this is O. Now where normal stress is maximum, this point, that is OG, represents maximum normal stress, because here normal stress is maximum. So sigma max, maximum normal stress is OG. That is what? OC plus CG. OC is what? OC is the C is the center, and this is, we know that, sigma average, which is sigma xx plus sigma yy by 2. This is the C is the center. And what is CG? CG is the radius of the Mohr circle, that is also equal to OC plus CA. OC plus CA. What is CA? What is CA? CA is nothing but C root over C square plus A square. C square is sigma xx minus sigma yy divided by 2 whole square plus tau xy square. So let me write down the values. OC is sigma xx plus sigma yy by 2 plus root over sigma xx minus sigma yy by 2 whole square plus tau xy whole square. So this is the value of sigma max, that is maximum normal stress. So what is minimum normal stress? Sigma mean minimum normal stress is OH, this much. That is also OC minus CH. CH is nothing but CA, that is also the radius. CH is the radius. So OC minus CA. So sigma mean becomes what? Sigma xx plus sigma yy divided by 2 minus of this term, that is sigma xx minus sigma yy by 2 whole square plus tau xy whole square. So the values of sigma max comma sigma mean, sigma max comma sigma mean, these are called the principal stresses. Values are sigma xx plus sigma yy by 2 plus minus root over sigma xx minus sigma yy divided by 2 whole square plus tau xy whole square. So this is the expression for principal stresses. This is the expression for principal stresses. And the plane on which principal stresses act are called principal plane. Principal plane. The plane on which principal stresses act. So which is the principal plane? This is the principal plane on which principal stresses are acting. So A is nothing but A is what? A represents phi equal to 0 degree. State of stress at phi equal to 0 degree. So what is the orientation of principal plane? If principal plane is denoted by 2 phi p in Mohr circle, 2 phi p in clockwise direction. So clockwise direction 2 phi p, then tan 2 phi p. What will be tan 2 phi p? Tan 2 phi p is AE by CE. What is AE? So tan of 2 phi p is AE divided by CE. AE is what? Tau xy and sigma xx minus sigma yy by 2. So that is 2 tau xy sigma xx minus sigma yy. So tan of 2 phi p is 2 tau xy sigma xx minus sigma yy. And here we have to observe one thing. This rotation is along clockwise direction, so it will be considered as negative. This rotation of plane is negative because this is in clockwise direction. So this is the expression for orientation for principal plane. So this is the orientation of principal plane. So we have calculated the value of principal stresses. This equation gives the values of principal stresses, very important formula. And this is the orientation of principal plane. The plane on which principal stresses are acting is called principal plane. Now the next point is, what is maximum shear stress? What is maximum shear stress on the Mohr circle? What is the maximum shear stress? Maximum shear stress. What is the maximum shear stress? At this point here, this is the maximum shear stress. Say J. This point is J. So tau max is nothing but Cj. Tau max is Cj. Tau max is Cj. What is Cj? That is the radius of the Mohr circle. So Cj is radius of Mohr circle. So Cj is radius of the Mohr circle. Maximum shear stress is Cj. Now what is the value of Cj? Let us come to the figure. So Cj is what? That is the radius of the Mohr circle, which is nothing but Ce square plus Ea square. So Cj, that is tau max, is Cj, that is root over Ce square plus Ea square. What is Ce? What is Ce? Ce is sigma xx minus sigma yy by 2. That is sigma xx minus sigma yy by 2. That is Ce. So this whole square plus, what is Ea? Ea is nothing but tau xy. So plus tau xy square, root of that. So the expression of tau max, that is nothing but the radius of the Mohr circle, and the expression is sigma xx minus sigma yy by 2 whole square plus tau xy square. So this is the expression of maximum shear stress. Now we have to note another point. To note that, let us move to the figure. Here the principal plane, this is the principal plane, this is the principal plane, and we can observe that at principal plane shear stress is 0. So we have to note another point, that is at principal plane, at principal plane shear stress, that is tau, is 0. At principal plane shear stress is 0. This figure, let us come to this figure. Now say one has been asked to calculate the stress values on a plane whose normal makes angle phi with the x-axis, that is n phi, and this is sigma xx, this is sigma yy, this is tau xy, that is tau yx. So what we will do? So here this line AB represents phi equal to 0. So AB represents what? Phi equal to 0 degree. If this rotation is in counterclockwise direction, then we will rotate CA by 2 phi degree in Mohr circle, and we will plot this point D. The coordinate of D will give the values of stress on that plane, and if we want to calculate complementary stresses, then this will extend D to D dash. Coordinate of D dash will give the values of complementary shear stresses. So this was about Mohr circle of plane stresses. For the state of plane stress shown in the figure, this is the figure, determine problem A, that is the principal stresses and orientation of principal planes. And in the figure it is given sigma xx is 120 MPa, sigma yy is 40 MPa, and tau xy is 30 MPa. So we'll determine principal stresses and principal planes from Mohr circle. So let us draw the Mohr circle for this stress situation. Sigma xx is 120 MPa, sigma yy is 40 MPa, and tau xy is 30 MPa. So first of all, draw the sigma n and tau axis. Now point A, this is point, say this is point A, which is 120 sigma xx comma tau xy, that is 30. Next point B, that is 40 comma minus 30. Say here it is 40. So coordinate of point B is 40 comma minus 30. Now join AB, and this is the C. C is the center of the Mohr circle. Now draw the Mohr circle, center C and radius CA. So we have drawn the Mohr circle. Now which plane is principal plane? Say this is O. First let me give the names. This point is E, this is F, this point is G, and this is H. Now what are principal stresses are sigma max and sigma mean. So sigma max is OG and sigma mean is OH. And if we calculate from the geometry, we will get that is sigma max is sigma xx plus sigma yy by 2 plus root over sigma xx minus sigma yy by 2 square plus tau xy whole square. So this is the value of sigma max, where this is OG. OG is the sigma max. Now let us put the values. All values are given. Values of sigma xx, sigma yy and tau xy is given. So we can easily calculate sigma x. Sigma max. We can easily calculate sigma max. So sigma max becomes sigma xx is 120, sigma yy is 40 by 2 plus root over 120 minus 40 by 2 square plus 30 square, and that becomes 80 plus this is 50 this is 40 square. 120 minus 40 is 80. 80 divided by 2, 40 square plus 30 square is 50. So sigma max becomes 130. So sigma max becomes, this becomes 130. So 130 MPa. Sigma max is 130 MPa. Now what is sigma mean? Sigma mean is nothing but only this sign will be minus. So sigma xx, sigma xx plus sigma yy by 2. This sign will be minus only. Remaining all are same. Sigma xx minus sigma yy by 2 square plus 30 square. So if we put the values, this becomes 80 minus 50. So that is 80 minus 50 is 30 MPa. So sigma mean becomes 30 MPa. So we have determined the values of principal stresses. Max is 130 MPa, mean is only 30 MPa. So let us come to here. OH. OH is sigma mean, and you will get sigma mean. OH is nothing. OG is OC plus CG. OC plus CG. And here OC, this is OC minus CH. CG and CH are same because both are radius. So this is also OC minus CG. So this is the, from geometry we have already calculated that sigma max and mean, that is we have calculated the principal stresses. Now what is the orientation of principal planes? What is principal plane? Let us move to the Mohr circle. So principal plane is the plane on which principal stresses are acting. That is this plane. This plane is principal plane. This is, say, P, principal plane. Now where phi is 0, point A represent the straight stress where phi is 0. So this line shows phi is 0 degree. So this is phi is 0 degree. Now what is orientation of principal plane? That is, say this is 2 phi P. P represents principal plane. Let me write down it once again. This angle, sorry, this angle is 2 phi p. This angle is 2 phi p. Then tan 2 phi p is what? AE, AE divided by CE. What is AE? AE is tau xy, that is 30. CE, CE is sigma xx minus sigma yy by 2, that is 120 minus 40 divided by 2. So tan 2 phi p becomes 30 by 40. Let us move to the next page. We'll calculate there. Tan 2 phi p is 30 by 40, that is 3 by 4, or 2 phi p. From this 2 phi p is 36.86 degree and 180 degree plus 36.86, that is 216.86 degree. That is, we are taking two values. This is one, another one is 180 degree plus 36.86 degree. That is phi p. Phi p becomes 18.43 degree and 108.43 degree. So this is the orientation of principal plane, and this is in which direction? This is in clockwise direction. So rotation is negative. So this is in clockwise direction. So we have determined both principal stresses, these are the values of principal stresses, and orientation of principal planes. Now let me show you the orientation of principal plane in a schematic diagram. That is, given state of stress was, this is 120 MPa in y direction, 40 MPa, this is tau xy, which is 30 MPa, so this is the given state of stress. Now the principal plane, this is the orientation of principal plane or state of stress at principal plane. This is sigma max, this is also sigma max, this is sigma mean, this is sigma mean, and this angle is phi p, where phi p is 18.43 degree, and for minimum shear stress where, that is another 90 degree, so and 108.43 degree. So this is the schematic diagram for principal plane. Now let us move to the next problem, that is problem B. The stress components exerted on the element obtained by rotating the given element counterclockwise through 30 degree. So where we have to calculate the stress values, that is, this is that plane. Now we have to rotate this plane counterclockwise direction, that is CCW, through 30 degree, that is along this is 30 degree, and we will do it from Mohr circle. So first of all, let me once again draw the Mohr circle. Let me once again draw the Mohr circle. A was 120 comma 30. Point B was 40 comma minus 30. Then join AB. This is C. Then draw the Mohr circle. So this becomes Mohr circle. Now this is the plane. This is the plane, or point A represents the state of stress at phi equal to 0 degree. Now we have to determine the stress components on a plane which is rotated by 30 degree in counterclockwise direction. So in Mohr circle, we'll rotate it by 60 degree. In Mohr circle, the angle becomes doubled. We know that. So let us come to here. So this angle is 60 degrees. This angle is 60 degree. And this is the point D. So what are the stress components at point D we have to determine? So first of all, let me denote the points. This is E, this point is F, this is G, this is H. And normal stress at that plane which is rotated by 30 degree, say this is GH, this is say I, this point is I. So normal stress at 30 degree plane is what? Normal stress is OI. And what is shear stress? Shear stress at 30 degree plane is shear stress at 30 degree plane is shear stress becomes DI. Or you can say that is we are finding the both stress components, that is say this is say XX on 30 degree, and if we want to find out YY, so we have to take the complementary stress, that is this point is D dash and this is J. So sigma YY 30 degree becomes OJ. So these are the stress components on a plane which is rotated by 30 degree in counterclockwise direction. Okay. Now what is OI? Let us calculate what is OI. So that is sigma XX 30 degree is OI, that is OC minus CI. Now we know this angle, that is this is 2 phi p, this angle is 2 phi p, this angle is 2 phi p, and 2 phi p was 36.86 degree, and that is another 60 degree. So this angle, this remaining angle becomes what? 180 degree minus 60 degree minus 36.86 degree, that becomes 83.14 degree. 83.14 degree. So this angle is 83.14 degree. So what is OC? OC we know that value of OC we know, we have determined earlier, that was 80 here, that is 80. So 80 minus CI. CI is what? CI is CD cos 83.14 degree. So that becomes sigma xx 30 degree becomes 80 minus CD. CD is the radius of the Mohr circle, and we have already calculated radius of the Mohr circle is 50 MPa. So CD is 50 MPa. CD is 50 MPa. So 50 cos 83.14 degree. That becomes 74.03 MPa. 74.03 MPa. Now let us calculate what is sigma YY 30 degree. Sigma YY 30 degree. That is what sigma YY 30 degree is OJ. This one. O to J. OJ. That is OC plus CJ. CJ. OC is 80. What is CJ? Let us calculate CJ. This is CJ. This is CJ. And CI and CJ is same, because due to symmetry CI and CJ are same. So we can take the value of CI also. So plus CI, that is 80 plus 50 cos 83.14 degree. And that becomes, from this you can calculate sigma YY 30 degree becomes 85.97 MPa. Now the next part is tau 30 degree. What is shear stress on that plane? Shear stress on that plane is DI. This is DI. So that is DI. What is DI? DI is CD sine 83.14 degree. CD sine 83.14 degree. And that comes 49.64 MPa. So we have determined all three stress components. That is, sigma xx 30 degree is 74.03 MPa. Sigma YY 30 degree is 85.97 MPa. And tau 30 degree is 49.64 MPa. Now let me show this situation by schematic diagram. That is, given state of stress is, let me draw it little bit below. So this is the given state of stress, that is 120 MPa. This is 40 MPa and tau is 30 MPa. So this is the given state of stress. Now plane which is rotated by 30 degree. So this is, say, 30 degree, and here the state of stress is, this is 74.03 MPa, and this is sigma YY 30 degree, that is 85.97 MPa, and this shear stress is 49.64 MPa. So this is the schematic representation, and this angle is 30 degree, which is in counterclockwise direction. So this is the solution to the problem. Thank you.